Okay, so in this one, I got a lot of feedback from people in the comments and things on my last few videos, and some were saying that some of my advice was a little bit vague, which is pretty fair enough, to be honest. It's kind of hard to give really tangible advice broadly about the whole exam, but people just wanted to see how I actually go about kind of breaking down section 3 questions. And so it's a little bit tricky, obviously, because the ASA material is under copyright, and so we can do worked examples to them, but then I can't actually have the question on the screen or anything. So what I've done is kind of adapted some questions. The idea here is it's not necessarily going to be this is how you should answer them. It's also obviously not going to cover everything in the test. I've just tried to pick a few questions that cover some of the more common skills. They're also graded so that the first few are kind of, I guess, very formulaic, and they move towards what we're seeing in the test, which is a lot of reasoning skills and that kind of thing, or a lot of deduction skills. That being said, they're all modeled off of real ASA questions. Basing that on my experience from sitting at way back in 2012, 2013, and then as well as preparing for March, looking at the practice material, and then also thinking about what I saw in the actual test on March as well. A lot of people have said that section 3 is drastically different from the practice material. I think people are divided on that. I didn't find that it really felt any different. When I was sitting it in March, I can't remember the specifics of individual questions, but I know that some of them felt very, very similar. Yeah, there was somewhere I was like, okay, I can see they've basically just taken the same question, they've just adapted it. I apologize if my voice sounds a little bit weirder. I'm a little bit kind of low energy. I'm normally not a very excitable person to begin with, but I had my COVID vaccine yesterday and it has absolutely hit me for 6, and I've got a gigantic fever at the moment, and migraine is probably not good to be looking at a screen, but I'm not one to relax. I'm very, very bad at leisure time, so we'll go through this anyway. Okay, so with this first one here, you'll find that it is very, very similar to some other ASA questions. So it's looking at rearranging formulas, but also looking at the use of units and dimensions as well. So we've got an equation that's been used to model the behavior of a gas is blah, blah, blah. Z, B, and C are all real constants, and P represents the pressure, V the volume, and T the temperature of the gas sample. Consider the dimensions of B and C in terms of fundamental quantities of mass M, length L, and time T. And then the dimensions of C are. So with this one, there's obviously not a lot of information to kind of process. Normally when I'm reading through a section 3 question, I'd be kind of trying to highlight to myself, making mental notes of what I think is probably going to be relevant to a particular question, particularly when they kind of make individual statements as their own standalone sentence. That usually tells me it's going to be significant. Here though, there's very little, right? So maybe the fact that it's to do with a gas, I might have to make some kind of assumptions, but I doubt it, given that it's an unfamiliar formula. The other thing then is I would just be paying close attention to how they've defined, or how I've defined in this question, mass, length, and time. Obviously, because T, capital T, normally represents temperature in most formulas, and time is usually lowercase t. So we've just got to be mindful of that. So the dimensions of C, this is more of a maths question than a chemistry question or a physics question. The concept here is that we've got these two brackets and we're adding or subtracting in each case. And so just like where you can only add and subtract like terms, you can only add and subtract values that have the same dimensions and the same units. Like a simple example is you can't just add something like $5 plus 3 meters or something like that. Doesn't make any sense, right? We couldn't say 8 because otherwise then what would the units be, right? So they're not like terms in a sense. So we can use this concept here and we can just isolate for C just this bracket. So if we're subtracting C from the square of volume, then technically the dimensions of C should be the exact same as the dimensions of the square of volume. Now, we're restricted, we don't have a dimension for volume specifically. We have to think about what dimensions that has. And so basics of volume is going to be length by width by height, but they're all versions of lengths. They're all length dimensions. So really volume is equivalent to length cubed. And so therefore, then if we square it, v squared, that would be length cubed for volume, and then that's going to be squared, and then we use an index law and we get L6, like that. And this should be the exact same as C overall. And so there, we know the answer then is D. The next one, the dimensions of B, we use the exact same strategy here. It's obviously a little bit more work going on. Just remove that out of the way. So in this case, now the dimensions of P have to be equal to the dimensions of this fraction here. Okay, and so there's something else that I actually missed in this. What I'm going to do is add in and temperature, and we're just going to measure that in Kelvin, even though technically it'd be something else. I realize there's an error in the question, so I'm just going to change that. We're going to have a fourth fundamental dimension. So if we go through question 2, so we're looking for the dimensions of B, we can say that the dimensions of P and the dimensions of this fraction should be equal to each other. And then what we're going to do is effectively solve for the dimensions of B. So for pressure, it's force divided by area, mass times acceleration over area. The mass is one of our fundamentals there. Now acceleration, think about its units, it's meters per square second. So that's a unit of length per square time. So we can say that as length and then t to the -2 for time. Remember, that's not temperature. Divided by area, and area is length times width, or in other words, the square of length. So L squared, and we can simplify that. And we can say, well, that is m, L to the -1, because we can use index laws, 1 take away 2, and then t to the -2. And that's going to be for the pressure component. We want to then make that equal to BT on V cubed. So BT on V cubed should be the same as ML to the -1, T to the -2. And then we're going to, again, work out what are the fundamental dimensions of each of these parts. B, we don't know yet. Temperature, which we're going to call K for its fundamental dimension. I'm kind of adjusting that slightly to make it work. And then the volume, we do that same thing, L cubed. This time we're going to cube that. And then we're going to solve for B. So just rearranging the formula. All right, and so this here would be B times K. We'd times, this would be L9, applying the index law and raising the power. So we can bring that up here, and I'm going to sneak it in here, L9, T to the -2, and then divide the K. And again, we've got index laws here, so we can go -1 plus 9 on the L's. It's going to be +8, T to the -2, and we're dividing the K across, so it's like K to the -1, like that. And then overall, we can see that that matches with option B. So a lot of these maths ones, I wouldn't actually do trial and error. It's very rare that you actually have to do trial and error. That's usually where people run out of time having to test every single one. You can do them that way and look for pattern recognition, but you'll be there for a really long time. So ideally create equations where you can and solve them, because it's just going to target and get straight to the point. And then the third one is not really fundamental dimensions. It's actually looking at units. And we're going to be using Kelvin for the units of temperature again, because it's the standard unit for it. And this relies a little bit on the use of standard units. So the units of Z, so this time instead of dimensions, we're going to look at what is happening in the first bracket. They should all have the same units because you're subtracting them, so they have to have the same units, be like terms. So again, what I can do is I can just take the units of pressure is going to be easiest. And then I've got to add that, I've got to multiply that. I'm just going to roughly loosely do this, because again, what you're working out doesn't matter. And it's multiplying by the volume squared, right? The units of each of these. And this will be equal to some units of Z multiplied by the units of temperature, which is K. And then we've obviously got to solve for Z and then match it. So pressure we did before, so that was force divided by area. So that is newtons, and then per square meter multiplied by, just get rid of that now, then this here is going to be meters cubed for volume squared is equal to Z times K. And so then here this is going to be newtons, meters to the -2 for this here. Meters here, we're going to raise the power, we're going to go 6, and then we're going to divide the K across, so K to the -1, and there's Z. But we can clean that up a little bit. Again, we can put the M's together, add those powers, and we get M to the 4, K to the -1 is equal to Z. Make sure that looks like a K, like that. And we can see it's still not there though. This is what they often do, right? So they want to see if people can just manipulate it to the form they need and effectively jump the gap to the answer at the end. So at this point, I'd be looking and going, okay, Well, k to the negative 1 is pretty common between the three, so it's very unlikely to be D at this point already. Commonality generally works quite well, but I wouldn't rely on it. But that means I'm not going to fuss about trying to restate the k to the negative 1. I'm going to focus on what's happening at the front here. And I'm going to look at what they did. They got joules and meters cubed. So meters cubed means they dropped down 1. And I could do that. I could go, well, newtons times meters cubed, just kind of split that 4 out a little bit. And then I can see, there's torque, Newton meters, right? And another way to think of it is that is force multiplied by distance. And force times distance is work, right? And work is a measure of energy. And we measure energy in joules. And so really we've got joules, and then we've got meters cubed per Kelvin, like that. And then that actually does match on that one there, like that. So the trick in C is that it's joules and then liters, but even though cubic meters is a measure of volume and so is liters, liters and cubic meters are not the same, right? It would have to be, if it was to be in liters, then it would be 1,000 liters. So there'd have to be a number 1,000 in there, because there's 1,000 liters to a cubic meter, so do watch out for that. And there we go, and that's that one. So that one's very much an algebraic set of questions. The next set then, so now we've got here, the ideal gas law. This is one that I wrote up during my practice. This one's a little bit more kind of straight up chemistry, so less likely to come up. But as we go through, you'll find they're not really just about calculating numbers, it's about understanding the relationships between the variables. So the ideal gas law PV equals nRT describes the volume occupied by a particular amount of gas at a particular temperature and pressure. For a 200 ml sample of carbon dioxide gas at 25 degrees Celsius, which of the following is closest to the mass of carbon dioxide gas that would be present if the sample is held at 325? So again, standard units, do watch out for them. Ignore the typo that I made there. Except this one would need to be put into liters, so 0.2, and we've got some decimals coming up. And so just like I did in my last video talking about ways we can get around that, we'll see how we go. We're looking this time for the mass. So I know that the number of moles is directly proportional to the mass, and I've got the carbon dioxide, so I know what the molecular mass is, and I can multiply them at the end. So if I solve for n, I can just divide the RT across, and if I wanted to, I could just go, well, mass is molecular mass times number of moles. So I can just put the molecular mass into the formula as well, like that, and then just do it all in one hit. So the pressure was 325, the volume was 0.2, which is 1/5, that might be helpful. And then carbon dioxide, so CO2, so we've got 12 plus 2 lots of 16 or 32, 44. So we've got some pretty ugly numbers at the moment over R, which is 8.31. They would normally probably give you that in the actual question. They don't really care too much, so I'm just going to call it 8.3, and then multiplied by the temp. And again, the temperature, watch out here, it's 25 degrees Celsius, but we want it in Kelvin, 298. And so again, I look at the numbers and they're all pretty different from each other. Maybe like 10 and 50 are pretty close, 50 and 100 by scale, but this I'm just going to go, let's just call that 300. This I'm going to call 1/5. Then here I can go 44, call this 8. I'm drawing connections between the 44 and the 8. And then this I'm going to call 300, like that. And so I have rounded down and up here, which is probably starting to increase my error margin, but even still, the relative difference between these, it should be fine. If I need to, I can always go back and add in the 25 and adjust if I'm not sure. But for now, I'm going to cancel those out. And then here, it's going to be 1/5. I might actually go for 1/5 divided by 8 first, which gives me 1/40th, because then when I times that by 44, it's basically 40 over 40, so it's effectively 1 gram, right? And even though I've rounded, I don't think it's going to be 10 at that point. That's 10 times greater, and the relative difference that I made here is not a difference of a factor of 10, so I can kind of make that assumption there. That's the kind of reasoning that you can use to work quickly in the maths, and so this is approximately 1 gram, and then our answer will be C. You could also see that here, you could do this as 1/5, and then you could go 325 times 1/5. The 25 divided by 5 is 5, and 300 divided by 5 is then going to be 60. So you get 65, and you could play around with that, but you can see it's not going to have huge impact. The next one, consider a given inert gas with initial pressure PI, volume VI, and temperature TI. Which of the following is the correct ratio of final pressure to initial pressure if the temperature is tripled and the volume is halved? So this is a proportionality question right the way through. And so the way that I would tackle this one is I would basically go, all right, well, I need the ratio of final pressure to initial. So I'm just going to set up an equation. I'm going to put the rearranged gas law for each of them immediately over the top. So there's a couple of other ways which I might go through as well. So if PV equals nRT, then pressure is nRT over, can't get it right, over V. So the number of moles is constant, right? So that technically is going to cancel. I'm just going to write it in there though. The R is constant, that's going to cancel. The temperature apparently is changing because the temperature was tripled. So I'm going to put that in as T final over volume final, all divided by, and the same thing, nR T initial volume initial. And you can see now the n's cancel because they're constant, and I get T final over V final, and it's divided by this fraction T initial over V initial. So I'm going to times and flip that like that, and now I've got my ratio, and then I just have to put my factors in, right? So the temperature is going to be tripled. So what that means is that T final over T initial is 3. So therefore, what have I got? I've got T final over T initial just here. There and there. So I'm going to replace that with a 3 multiplied by, and then the volume is halved. So that means that V2 or V final over V initial is half, right? I've actually got VI over VF, so I can just kind of flip it around. So I've got 2 over 1 then for V initial over V final. So then I can put this, I might color code that. These two here are going to give me 2. And I get 6, like that. And so this is the final to initial, so always check the ratio. What is the ratio of final to initial? 6, and therefore 6 to 1. The answer is A. Right, and so, yeah, so some other ways as well. You could also do proportionality, so you could go P is, that's a bit messy, I'll just do it over here. You could do P is directly proportional to nRT over V. Since N and R are constant, then you can just go P is proportional to T over V, and you can just kind of shortcut it right there without all the algebra. Probably saves you a bit of space, and it'll give you the same answer. All right, so yeah, in fact, yeah, you could do it. Actually, it's a lot quicker because then you could just do it like this. That's tripled, that's being halved. It's directly proportional to 6, so therefore P final is 6 times P initial, and then bang, nice and quick. The molarity of a given gas mixture can be represented as. So in this case, molarity is obviously another measure of concentration. So that is going to be number of moles divided by volume. So if we get PV equals nRT, they trick you here because we're so used to solving things for one of the existing variables, but you can solve for a combination of variables. So I basically want to get N divided by V on its own. So I can divide the V across. So nRT divide the V, and that's equal to P. But then I have to divide the RT back this way. And there's my molarity. So that would be, written in another way, P and then the inverse of RT. And there, see, you can start moving through them quite quickly like that. The next one then, so a sample of an unknown gas has a mass of 34 grams, so M, and occupies, so what I'd be doing on the scratch paper here to run you through, I'd be listing M equals 34, immediately converting to exact or standard units where I can. Occupies a volume of, so V is equal to 0.8. I often leave out the units if I'm working in standard units anyway. Temperature is going to be 30 plus 273, so 303, and 200 kilopascals of pressure, so P 200. Which of the following is the closest estimate of the gas's molecular mass? So we had this trick before where the molecular mass can directly relate to the number of moles and the mass itself. So since mass is equal to n times molecular mass, we can say that molecular mass is mass divided by the number of moles. Where do we get the number of moles? From our gas law. So PV equals nRT, and so N is equal to PV on RT. We dump that into here. We get molecular mass is that divided by, now I'm writing out every step, but realistically I'd be skipping steps to save space on the scratch paper, times and flip, and now we've got an equation for the molecular mass, and we just dump all of our numbers in. So most of the work is actually just in the rearrangement. So 34, now we've got to actually do the maths on it though. 8.3 for R, temp was 303, pressure was 200, and then the volume was 0.8. There we go. So now again, I'm looking for ratios. So I'd say 8, just ditch the 0.3, 8 over 0.8, that gives me 10. And then 300 over 200, about 1.5. And then here I'm just going to go from there, 10 times, I'll probably go 10 times 34 actually is 340 times 1.5. Then in my head I'd just be going half of that is 170. So 340 plus 170 is then going to give me 410, 510. And there we go. And obviously this is what is closest. So that is closest. I've got a rounding error, so that's probably why it's not exact. And they may not even be giving the exact values either. So, but I know I'm in the ballpark. There's nothing else that's even close to that. So now questions 8 to 9. So this one on partial pressures, the initial contributing pressures of each gas component and mixture of gases held in a single container. Each gas's partial pressure, Px, is proportionate to the mole fraction of the gas mixture. So I'd definitely be paying close attention to that. This is just using, I think it's Charles' law from memory. Can never remember the names of them. But it's just saying that Px is directly proportional to the number of moles. So the more moles, or the more mole fraction you have actually in total, the bigger the proportion of the mole contribution, the bigger the proportion of the pressure contribution. We've got a particular gas equilibrium mixture of nitrogen monoxide with nitrogen gas and oxygen is shown below. We've been given a K value as well. A particular mixture of the above equilibrium system is formed by introducing. We've got number of moles of nitrogen, 0.05 moles of oxygen in a 2-litre container, and then is left to reach equilibrium. If the pressure of the final mixture is 1 atmosphere, which of the following ranks the 3 gases in order of increasing partial pressure? So because I know that partial pressure is directly related to the number of moles, I'm not actually going to go all the way to calculating pressure. In fact, I really don't need to. Once I've got the rankings of the number of moles, I can rank them based on their pressure. And these apparently are all going from lowest to highest. So because it's an equilibrium mixture, I need to do an ice table. And so we've got N2, O2, 2NO, like that. We're told at the start we have 0.2 moles of nitrogen and 0.05 of O2, 0 of this. We've got a K value, so this is going to lose X amount, this is going to lose X amount, this is going to gain 2X amount, and then the equilibrium will be 0.2 minus X, 0.05 minus X, and 2X. Now keep in mind these are moles, so then from there we've got to divide them because you can only put concentrations into the K equation. So then you've got to divide them by their volume. So divide by 2, divide by 2, divide by 2. And I would simplify this, right? It's just going to be a lot easier. 0.1 minus half x. This one over here, 0.025 minus half x, a little bit messy. And this one's going to be x. And this is our product. So the K is going to be the concentration of NO squared over the concentration of N2 times the concentration of O2, all at equilibrium. And so we put our numbers in, so we get x squared over 0.1 minus 0.5 x times by 0.025 minus 0.5 x, like that. And that apparently is equal to 2.34. Sneak over here. Oh, 2.34 by 10 to the negative 3. So this is a bit of a tedious one. We always assume that x is relatively small though, so you pretty much get to just, I mean, that's really, really small. So you just assume that this is effectively 0 and it doesn't play any role. And you just do this times 0.025. It won't play huge impact in it, only when k is really small, but they pretty much always make k really small. So then you don't have to deal with quadratics. It's not really a focus of the test. Then we've got x squared is equal to 2.34 by 10 to the negative 3. I'm going to multiply this over. So a tenth of this is just going to move the decimal point across a bit more. And then I'm going to work this out. So working with exponential formats, I would actually convert this to 2.5 by 10 to the negative 3. So now I can just deal with the numbers. And it's like 2 and a bit times 2.5. So 2 times 2.5 would be 5. 0.3 of it, I'd probably go, well, 3 times 25 is 75. So then I'd estimate and go, it's probably 0.75. So 5.75. And then index laws on these two, 10 to the negative 3 times 10 to the negative 3, 10 to the negative 6. And then lastly, I've got to square root it to get x like that. And oh, it's really messy. And then I've got to square root that. So square rooting this, it's just going to halve that back down to a negative 3. And square rooting this, square root of 4 is 2. Square root of 9 is 3. So this is closer to 4. So I'm going to say it's around about 2.3. Complete estimation. It's going to be my x value. And so then what that allows me to do is rank them. So even though we said x was approximately 0, and so really the final concentrations, or the final amount, sorry, the final number of moles of nitrogen is pretty much still going to be 0.2, oxygen's still going to be pretty much 0.05, but it is important to note what is NO. It's going to be 2 times this amount. Yeah, which is still going to be way, way smaller. So overall then the NO is going to be the smallest. Then after that, the next smallest is the O2, and then lastly the N2. And that's by number of moles, but that is because it's proportional to the partial pressure. This would rank the partial pressures as well. So therefore, partial pressure would be A, like that. All right, I'll just remove this out of the way for the next one. So then it says the partial pressure of NO at equilibrium with 2 liters volume is approximately. Okay, so the partial pressure of NO, they said the final mixture was 1 atmosphere. We've got 0.2 mole plus 0.05 mole plus the 2.3 by 10 to the negative 3 mole altogether. That's the entire number of mole of stuff that we have at equilibrium. So this would be 0.25 plus this would be 0.0023. So then that'll be 0.2523 mole. And the proportion of NO by number of moles is going to be that 0.023. So 0.0023 out of 2523, and that should be equal to the same partial pressure of NO out of the 1 atmosphere of total pressure. And you can see all the answers are a fraction of atmospheric pressure. So we're really just looking at what is this as a fraction. And so what I would do in this particular case, dealing with the decimals, is just move the decimal point across until you get a whole number. So I'm going to move that across 4 spots till it becomes 23. Do the same to the bottom, like that. And then just kind of clean it up. So go, well, that's like 25 over 2500. It's not really going to matter if you look at the difference between all these fractions. So then the 25 can cancel to a 1. You get 1 out of 100, like that. This does say approximately, right? So I've purposely written it that way just to mess with the answers, but 1 out of 100, we basically go for the smallest one. It's definitely not 1 atmosphere. 1/5 is way too big. 4/5 is definitely too big. 1/50 is as close as we're going to get. Really, it's going to be 100th. All right. So now we start getting into more of the ones that rely on graph reading and reasoning rather than just pure calculation. So being able to read graphs is a really, really key skill to be able to move quickly. I've talked about this before, but now I'll be able to actually kind of use an example. What I do whenever I'm reading a graph is I look at what variable is like the independent variable, so to speak, and I try to hold everything else constant and then try to scan through the graph where my independent variable is changing. So if I was interested in understanding the impact of arterial blood pressure here, we'll go through the question in a moment, then that means that I need to scan left to right, but hold everything else constant. So for example, I might want to stay at the same Y level, like that, and then scan across and then see what's happening to other things. So for example, what is happening to arterial blood proton concentration, or what is happening to these lines, which is going to be the partial pressure of carbon dioxide. Like that. I might zoom that in a little bit so it's a bit easier to read. There we go, hopefully that's clear. So here we've got blood pH can be altered by a varying partial pressure of carbon dioxide, PCO2, due to the formation of carbonic acid in the blood. The first association reaction for carbonic acid is as follows. Figure 1 is a chart showing the different blood pH disorders and their pH concentration and partial pressure boundaries. Get rid of that now. So what is the minimum partial pressure of carbon dioxide that would define chronic respiratory acidosis? So when I'm going through the graph, what I'd be doing is just kind of very loosely looking at what information is being presented. So I'd be making a note of the fact that we've got a bunch of different diseases or a bunch of different illnesses, and then we've got, I can see 3 axes around the outside. Then we've got those lines going through it. They like these graphs a lot now. So I'd be making a note of that. I want to hold everything else constant and then look at what the impact of one thing is at a time. So here it's what is the minimum partial pressure of carbon dioxide. So it's those purple lines that would define chronic respiratory acidosis. So I look to chronic respiratory acidosis, try to understand like what region, right? Because it's very vaguely positioned, but it looks like each of these kind of branches or arms is supposed to represent one of the illnesses. And so in this case, we want the minimum partial pressure. So I want the lowest partial pressure. I then scan around each of those lines and look at where it's decreasing. So I look to the lowest and I go, okay, so literally physically lower down on the graph means lower. Then I look at chronic respiratory acidosis. I'm ignoring all the other axes because they're irrelevant to me. And I'm just looking at the purple lines. How low can I go until I go beyond the boundaries? And I would probably take that line because it's right on the cusp of that corner before it suddenly becomes metabolic alkalosis or it becomes normal as well. So that would be the most logical answer there. And then I would confirm that the answer is there. So that's that line. I trace it up and it says 50. And there is an answer there. Then I would check what else is there just in case. So 40, right? That's clearly well beyond chronic respiratory acidosis. So anything below that is no good. And then it's got 110, right? And 110 is the wrong way. That's high. And that's good feedback to me because then I know, okay, that's the reason why that one's wrong. I would often try to reason out the tricks in the other answers so that I could be sure that I've kind of not been tricked by their questioning in any way. Cool. All right, so that's that one. Then someone with a partial pressure of CO2 of 20 millimeters mercury, blood pH of 7.25, and arterial blood plasma of carbonic acid, or at least the first association of it, of 8 milliequivalents per liter, will be experiencing which disease? So this one is just about like reading the graph, basically using the chart. So the first thing is I'm going to go, okay, I've got my 20 mils. So I'd be highlighting that. I know obviously difficult on the screen, but I remember I was putting my hands up to the screen, like a couple of possible diseases there. But then the next thing was it said a blood pH of 7.25. So I find 7.25, which sits here. And I'm pretty sure now I've got metabolic acidosis, but I'll just keep going just to be sure. So they're crossing over. I'm looking for where they're all crossing over. And then arterial blood plasma of 8 milliequivalents. And that one's the left axis. And I go, yeah, perfect. They're all lining up. Again, that's good feedback to me. And so therefore that is metabolic acidosis. like that. Cool. Yeah, so then it's going to be C. So that's more of a graph reading one. And so then this final one I put together. So I have seen there's a bit of a trend where they use, I guess I'll call them like related graphs, where you have 3 or 4 graphs and the variables all kind of interconnect in some way. And then you've got to kind of make deductions about them, kind of reading across multiples of them. So we've got white-browed sparrow weavers, or the Latin name, I'm not even going to attempt to try and read that, a species of bird found throughout central and north-central southern Africa. They're often found in groups containing one breeding pair and the remaining individuals non-breeding. So it almost sounds like that's going to be focused on, and truthfully, if I was reading this, I would think, okay, maybe there's something to do with reproductive strategies, or maybe they're going to go into genetics or that kind of thing, but it doesn't actually go that way. A study into the effects of air temperature, TA, and humidity measured in grams of H2O per cubic meter on the internal body temperature, TB. So you can see that it's defining lots of different labels. And I found that I got really confused when they started using a lot of jargon and like using a lot of acronyms that you had to just kind of immediately keep up with. So what I would do on the scratch paper is I would just write down a little key, so I didn't have to keep searching through the paragraphs. They often hide everything in the paragraphs. That's why I've done it in this way. I might even put like humidity in terms of what it's being measured in per cubic meter. TB was body temp. And then EWL, I'd literally just put water, right? Because there's nothing else to do with water. Per hour, so I'll put grams per hour. Resting metabolic weight, so I'll just put met, and that's measured in watts. And the evaporative heat loss, so EHL, I'll just put the word heat next to it, and the metabolic heat production, and I'll just leave that one off. So then we've got the following graphs summarize the findings. The dashed line in the first graph shows the line TB equals, that should say TA actually. There we go. All right, cool. So we've got all these here. We'll zoom in so that we can see them a bit more clearly. But first of all, so which of the following situations would place the greatest energy demands on the bird? So we have to first work out, all right, which of the graphs is going to relate to energy demands? So if we do zoom in a little bit now, we can see body temperature. There's no mention of joules or anything, so that wouldn't be related. Evaporative water loss has nothing to do with energy demands. Metabolic rate does. So we've got watts, right? This is joules per second overall. So this is probably the most helpful. And this one was evaporative heat loss and metabolic heat production. So again, that's to do with heat. Yes, there's energy in there, but we don't have a direct measure of it. We don't have any units for what this is. So we can't actually like have any kind of numerical calculation there. So I'm going to look at this graph, and then it says, which of the following has the greatest energy demand? So effectively, which has the highest metabolic rate? So we've got a bunch of different ambient temperatures and then different humidities, and we're just going to literally just locate them. So again, this is a bit more of like a graph reading one. So we've got TA of 42 and humidity 13, and we use the key. 13 is green, like that. I'm just going to circle as I go. If you're on the computer, then I'd just be holding my finger on it, and then if one goes higher, then it means that I just move my finger to that one. Higher literally just means vertically higher. I don't have to worry about left or right because that's air temp. I'm just looking for the one that sits at the highest level. I might even put a note like that's option A. B, 41 and 25. So 41 and 25. 25 was dark blue. That one's there, so that one's now winning. Then 44 and 6. Just down there, that's definitely not winning. And then 41 and 13. Which doesn't even matter. All of them are below that other one. 13 was the green, like that. So it was option B. That one's not too bad. The next one then, further studies into the interrelatedness of the 4 variables measured are suggested to be conducted. Which 2 variables may show correlation that would undermine the hypothesis that all 4 variables are dependent on air temperature? So this is a really, really tricky one that I've put together here. So basically, it's kind of testing empirical research skills, like understanding the scientific method. So the hypothesis of the study was that air temperature was the independent variable every time, and that was what was causing the changes in all 4 of these measured variables in the graphs. But then we're looking for what pair of y variables or dependent variables may actually have some interrelation between them. And it may not actually be air temp, it may be those 2 that are contributing. So, or one's affecting the other. And so effectively what you have to do here is look at which 2 graphs actually have the same shape or the same rough scatter. The idea is then that if they're trending in the same way relative to temperature, it may be that they're just responding in an equal way to temperature, but it may be that it's one is actually directly impacting the other, and that's why they're trending in the same way. So if we look through, I probably wouldn't try to look for the trend myself. For this, I'd probably test each of the options and then just see which one has the closest connection, because it's somewhat ambiguous. Resting metabolic rate and EHL MHP, so that's these 2 here, clearly completely different scatter plots there, right? So there's doesn't seem to be any direct correlation between this variable and this variable. In fact, you can even see like the yellow line going down slightly, while here the yellow line going up. Then we've got EWL and EHP MHP. So EWL was this one, so it's just kind of using all of that jargony stuff. Looks a little bit better, they're both trending up, but in general, most of the graphs are trending up. So we'd put that in the maybe pile. Then we've got body temperature and EWL. So these look a lot more similar. And you can see some of the features, for example, you've got this kind of almost outlier up here, appears to be higher than the others again in this group. And then the yellow also seems to be following this kind of S curve through it as well. And you can see some of those common trends. Green generally stayed above the yellow. Green stayed above the yellow. So I'm just kind of looking for basic interactions and just breaking it down into bits rather than the specific numbers themselves. Just looking at shapes, and it helps me kind of analyze the graph a lot faster. And so that one's probably looking even stronger. You can even see that before we said EWL and EHP, these 2, see how yellow here was above, and then here yellow was actually kind of below. It was in the middle. So that's a point down for B, starting to not look like it's right. Then lastly, we'll look at the last one, resting metabolic rate and EWL. So these 2 here. And again, this one's very different. So it's got no correlation there between them. So the answer will be C in that case. And then 15, which of the variables was most impacted by changes in humidity? Okay, I'll get rid of all of this junk. So this one, this is what I was talking about at the beginning. I'll just put that back. So this is where you're trying to hold all other variables constant, and then you're trying to see the impact of one variable. In this case, I want to see what is the impact of humidity. And then it depends on which one I'm looking at. So the first one says resting metabolic rate at low temp. So I'm going to go to resting metabolic rate, and I'm going to go to low temp, which kind of means this region. And then it means holding all else constant, increase or change the humidity. So basically that just means go yellow, green, light blue, dark blue. And then I increase the humidity, and I'm going to see what happens to the resting metabolic rate. So I'm going to keep the air temperature constant. So I'm going to go up this line here, yellow, green, there. That seems to go up a little bit, right? So that does seem to be somewhat impacted. This one here, yellow, and then all of a sudden no change. They're all kind of the same. There doesn't seem to be any more impact. As I increase the humidity, the resting metabolic rate doesn't actually change at that temp. So that's not looking very strong, because this is most impacted. So there's some impact, but really only at this temp, there's a little bit of change. I'll get rid of all of that again. The next one then, resting metabolic rate at high temp. So we'll come over here, and again, yellow, green, light blue, dark blue. So yellow, green, light blue, dark blue, that's a lot of change. Yellow, green, light blue, and I don't think we have a data point for dark blue, but again, we've got very consistent increases, right? That one went zigzag back and forth, but might be a bit of an outlier. That one's looking pretty promising. Then EHL at high temp, so evaporative heat loss, that's this one over here. High temperature, and again, we can go the other way, so we can go downwards, so yellow, green, light blue, dark blue. So yellow, green, light blue, dark blue. It went back. It's not great news. This one here, yellow, green, and only a little change. This one had much bigger moves. What I'm doing there is kind of looking at where I had the biggest vertical leaps. So here I'd be literally looking at the physical lengths or sizes of each of those variations. So from yellow to blue, it's quite a big jump. This one had that big of a jump, whereas over here, collectively a lot smaller. So still B's looking like the strongest answer. And then body temp across all air temperatures. Body temperature, you can see very little variance here at this temperature. They're just kind of bouncing back and forth. They're all kind of around the same point, which means humidity is not really impacting the body temperature much. It's just the air temperature that's raising it overall. And so there we go. So the answer is B. And so that's what I mean by holding all other variables constant and just varying one thing, right? Look for that variable, look to which direction is increasing or decreasing, and then see what it does to the other variable of interest. The impact on air temperature of an increase in metabolic rate. That would mean we want to keep the humidity, the unmentioned variable, constant. And so in that case then, I'd just pick a variable to start off. Let's pick the yellow, right? And I'm going to see what happens. Like that. No, it's not really working very well for me. There we go. So if I want to know what happens to the air temperature as I change the resting metabolic rate, what that means is I have to take I could take like a straight line like this, and I could scan downwards, right? This is something that I did as well. You can get a piece of paper and put it on the screen. As I decrease resting metabolic rate, what happens to the air temperature? It's like 39. Then the next one that I hit, there's like all three of them. There's one at 36, one at 40, one at 42, and then 44. So in general, that meant that as I reduced metabolic rate, temperature increased overall. And so therefore, as I increase metabolic rate, temperature decreases, right? That's an illogical connection to make because the air temperature is very clearly not responding to metabolic rate. But it just proves the point that you can analyze any relationship between any variables, and you can use this straight line method. You can also do it like if we did a vertical line test, then if we wanted to know what's the impact of air temperature, right? As we were doing initially, we just draw a vertical line like this. And then if we wanted to know what was the impact on metabolic rate, it would mean I'd want to keep the humidity constant. This time I might pick this one here. That just helps me visualize it. I'm just going to scan along. As temperature increases, the metabolic rate goes up. Like that, you can see that line is trending up. I mean, we can already see that from the actual scatter plot itself, but again, just proves that point. Okay, and so that then is, that's at least one sample of section 3 questions. I'll probably do more of these as well. It takes a little bit of time because I've got to actually write up the questions to get some fresh ones. But it's probably a good chance to get some access to some free questions as well. I know it's difficult to come across them. Hopefully these are, somewhat reflective of the ASA material. They're definitely not easy to write. And I know that ASA obviously put a hell of a lot of effort into writing their questions. As much as we hate them, they write good questions. The important thing to take from this, I think, is just some different ways or different perspectives to take when tackling section 3. You can see that there's a little bit like when you get to the maths and stuff, there's, you have to be able to just manipulate formulas, for example. But with like graph reading and that kind of thing, it proves the point you don't have to know anything about the specifics of what they're talking about, right? That it's there to overwhelm you. So like that one where they talk about where I'm talking about the white-browed sparrow weavers and stuff like that. It's all there just to throw you off. It's talking about Africa and the non-breeding, breeding. All that's irrelevant in the end, right? It's just seeing if you can take on a huge amount of information and sift out the stuff that is actually helpful to you. When you're reading it, you may not know what's helpful and what's not because you haven't read the questions yet. But as soon as you read the questions, they want to see if you can just kind of adapt to that change and start throwing things out the window that you can see are no longer helpful, because that's ultimately the kind of decision-making skills that they're trying to assess here as well. I'm going to put together, some people asked me for some practice questions to brush up on math skills and things like that. So what I thought I would do is put together a web page where I'll just put up as frequently as possible. It takes me some time to sit down and actually write them, but I'll keep updating them with skill sheets for maths and for more Section 3 questions like this, so that they're freely available. Like, I'm sick of seeing people charging ridiculous amounts of money for things. Like the fact that I think ACE are charging $45. I wish they didn't charge money for their practice tests, but when you can get ACE material for $45 and then you've got other companies that are charging thousands of dollars for courses, and really the only value in their courses is their questions. And at least from what I've seen from their sample stuff, because I never bothered to actually pay for their actual stuff, I might be wrong, but it didn't look to be up to scratch or of any real quality. So I think it's about time that there's resources that are put out that are actually freely available, because there's already enough financial burdens and enough financial barriers to get over to get into medicine. So hopefully you get something out of that, and let me know if there's something that I've missed in this particular video. If you want to see specific types of questions, I've probably focused a lot on chemistry and a little bit of biology here. We haven't done a huge amount of the physics side of things, so if that's something you'd like to see, I can do a specific physics questions based video as well. Otherwise, I will see you in the next one.